Hi everybody, welcome to this video on probabilistic seismic hazard analysis. This is building on previous videos where we talked about source models and also ground motion models. And before I get started, I want to give a shout out to the book Seismic Hazard and Risk Analysis by Baker et al. 2021, and also a series of videos on YouTube by Jack Baker. If you really want the nitty-gritty, you should check his stuff out. So in this video, we're going to just quickly talk about what is a PSHA. Then we're going to look at joint distributions that arise from complex rupture scenarios, epistemic versus aleatory uncertainty, and then how we can envision all of the possible scenarios using a logic tree. So the goal of a PSHA is to generate a seismic hazard curve. So this is essentially a relationship that predicts how many times per year we might exceed some particular spectral acceleration or some other ground motion parameter. So what we see is for low accelerations, we do that frequently, and for high accelerations like 1g, we do that very infrequently. And this allows us to predict the risk and help advise engineers and zoning specialists. So that's our goal. So what do we put into a PSHA? As I mentioned, there's two big inputs. One is source models and one is ground motion models. I'm just going to briefly touch on these here. So a source model is essentially trying to represent what are the possible earthquake ruptures that could occur. And these could come from faults. So we're going to rupture some portion of a fault. They could come from points, or they could come from areas. And it's very often the case where if we don't know a lot about the faults, we may model the source using just distributions of earthquakes within some broader area. Regardless of how we do it, whether it's a line or an area source, the goal is to come up with a relationship that predicts kind of, again, the frequency of earthquakes as a function of their magnitude here. Okay, and then the next thing we're going to combine that with is a ground motion model. So once we know something about the earthquakes themselves, we want to ask the question, what kind of shaking is that going to induce at our site of interest? And so these ground motion models typically are also represented by a curve that essentially relates some hazard parameter, typically ground acceleration, to the distance between the earthquake and the site. Okay, and what we see is that as distance gets bigger, the earthquake gets further away, the ground shaking falls off. But we'll see, and we have seen, that there's quite a bit of uncertainty around these predictions. And then we combine these things, and again, we get that seismic hazard curve that I already talked about. So one thing that's worth thinking about related to the combination of source models and ground motion models is complex rupture scenarios. And this is more and more happening with modern computing. And this is the idea that if you have a fault system, we really don't know usually what part of that fault system is going to rupture in the next earthquake. Is it going to be the whole system? Is it going to be the northern segment, the southern segment, or is it just going to be some subset of the segments represented by these individual panels? And so what we can do in these different rupture scenarios is we can develop statistical models that predict what the likelihood is of a rupture of some magnitude at some distance from the site. And this yields what's called a joint distribution. And this is a really cool plot. We have distance on this axis and magnitude on this axis. And the height of the bars represents essentially the probability of some rupture scenario of, such and such magnitude and such distance from the fault. And because this is done numerically, you can see it allows us to have some pretty irregular shapes and pretty interesting kind of assumptions and predictions. So for example, if you look at this, you see there's this line of taller bars at about 10 kilometers. This likely represents a large nearby fault that's capable of producing some different magnitudes depending on the rupture scenario. So if you rupture part of it, maybe you're going to produce some of these lower magnitude events, but if you rupture the whole thing, you're going to produce these big high magnitude events. And so the rest of the distribution, the joint distribution here, looks like kind of distributed sources throughout the region, whether they're other faults or whether it's the tail ends of the same fault. But it's interesting how we can generate these distributions. So a real-life example of this is the Wasatch Fault system. This is a system of normal faults that bound the western edge of the Wasatch Range. And of course, this is Salt Lake City right here. So the faults extend along the Wasatch Front to the north and the south of Salt Lake City, present a crazy seismic hazard. And a big question about rupture scenarios is which segments of the fault are going to rupture together? Are they all going to rupture in one big event? Or are they going to rupture in separate segments? And if they rupture as segments, how far are those segments from Salt Lake City? And so these scenarios can really inform our ground motion models. Okay, so I next want to just briefly mention some common terms, which are epistemic and aleatory uncertainty. So obviously in PSHA, there is a huge amount of uncertainty. It's really head spinning. And it's helpful to divide it into epistemic and aleatory, where epistemic is essentially, I think of it as, what are the known unknowns about nature, okay? What are the things where we're really just not sure what we should assume for the model? And we can also think of these as, look, the value or the model is going to be one thing or the other. We just don't know which. So an example of epistemic uncertainty, which segments are going to rupture during the next quake? Or what fault scaling model should we use to scale rupture length to displacement? There's been 4 or 5 of these proposed, and which one should we use? Which one is correct? Or another common one is, what slip rate should we assume for the fault? Should we assume a geologic slip rate? Or should we assume a geodetic slip rate from GPS? And if it's a geodetic rate, which model should we use? So these are all kind of black or white choices where we don't know which one is correct, and we'd like to be able to kind of include the different options in our final model. Now, aleatory uncertainty is different. This is what we're more familiar with. This we think of as essentially, hey, we already know the distribution, the probability distribution of possible outcomes, and when the event happens, we're going to pick kind of randomly some value from that distribution. But we already know what the probability distribution is. We just don't know what value we're going to pull from it. So a good example of that is essentially a ground motion model or an attenuation curve, where we are pretty sure the curve is shaped like this, but for a given distance, there's still going to be a lot of uncertainty on which exact spectral acceleration we get, and that can be represented as a Gaussian probability uncertainty. So essentially, we're going to, if we're 10 kilometers from the fault, from the earthquake, our spectral acceleration is going to be kind of randomly drawn from this Gaussian distribution, and that's aleatory uncertainty. So let's wrap up here by thinking about how do we use logic trees. And logic trees are fascinating, and here's what they look like. So we essentially start on the left with some rate of occurrence or some probability of occurrence, and we take that value and we run it through all of the different epistemic uncertainties, okay? So it's like a choose your own adventure type of deal. So we come in here, and this model component might be, what is the fault model? Where are the faults, right? Maybe you choose this map, maybe you choose this map, maybe you choose this map. Next model component might be, what's the slip rate on each of these faults? Next model component might be, what's the ground motion? So we run through each of these different models, and it lets us assign a relative uncertainty to each choice. So here we might say there's a 20% chance of model A1, 60% chance of A2, and 20% chance of A3. Then we move on to the next set of branches here. Oh, I have to say, notice these sum to 1, right? Each set of branches coming off a node, those probabilities have to sum to 1, because we're essentially stating this is a probability distribution, and there's only 3 choices in that distribution, and they have to sum to 1. Then we'll do the same thing over here. 0.1, 0.1, and 0.8, those sum to 1. 0.1, 0.5, and 0.4, those sum to 1. Okay, so after each node, the branches must sum to 1. Now, if we want to know the probability or the occurrence rate at the end of any particular terminal node, that's given essentially by the initial rate or probability times the probability at each branch. So this is 1 times 0.2 times 0.1 times 0.1. So that gives us a net probability or recurrence of 0.002. And that, so when we take that one, when we've completed this calculation for all of the terminal nodes, we essentially see that the terminal nodes themselves actually end up summing to 1, or at least summing to whatever value we start with over here. And they represent a complete joint distribution of all the possible model combinations. So we can essentially think of these as weights or probabilities of any of those given models. And there can be thousands of these terminal nodes. So I just want to bring this home with a real-world example. This is a logic tree used in the National Seismic Hazard Assessment, specifically considering the Wasatch Fault as a seismic source. And so let's look at the different kind of model categories they have. So first we split into 3 branches regarding what is the fault rupture model: full, partial, or floating. Then this one splits into 3 more. What's the geometry? What's the dip of the fault? 35 degrees, 50 degrees, or 65 degrees. And then these each split into what is the recurrence model? Essentially probably related to what's the slip rate on the fault. Then these split into what is that scaling model that we're using to go from probably rupture length to magnitude. And then these actually split into what ground motion model are we using. And you can see at each split, the weights all add up to 1. So one interesting question is, how are these probabilities or weights assigned, right? If we look at this kind of general logic tree from the National Seismic Hazard Assessment, we have, things like we've talked about: fault models. Where are the faults? Deformation models. How quickly are the faults moving? Scaling, maximum fault, all kinds of stuff. So there's a lot of decisions that need to be made, many of which are very subjective, you could say, and rely on the deep expertise of geologists or geodesists. So actually, sometimes these weights are actually assigned essentially by committee. Gather a group of experts together and discuss it and generate probabilities. And it's often thought that the weights should, quote, represent the center, body, and range of technically defensible interpretations, right? So that's what these experts are charged with. Experts, what's the most likely thing to happen? And then what are some of the end numbers that could happen? So pretty interesting to think about that. And then I just want to close the video. We just saw how logic trees can help us visualize all the possible models and kind of think about the probability of each model scenario. This can also be written more compactly, essentially as an integral, right? Where we can mathematically write that the rate of ground motion exceeding some specified ground motion is given by the integral, where we're going to sum up all of those possible rupture scenarios. So all the different rupture scenarios, and then for each rupture scenario, we are going to essentially multiply the frequency here, right? So this is that kind of source model, basically, by the ground motion model. You know, what ground motion is being produced by some given frequency. So again, integrate across all the sources, source model, the magnitude frequency relationship, times the ground motion model, and that's going to give you this final seismic hazard curve, essentially. The rate or probability, let's say rate, at which your ground motion is exceeding some threshold motion. So in conclusion, a PSHA combines source and ground motion models to generate seismic hazard curves. Ground motion models consider complex rupture scenarios that can yield joint distributions of magnitude and distance of rupture from the site. Or I should say these are rupture scenarios. Epistemic uncertainty arises from known unknowns. What is the fault model? What is the slip rate? Whereas aleatory uncertainty considers the probability of some outcome from a known probability distribution. Logic trees can define all the possible model variations such that the distribution of the essentially combined weights at each terminal node represents a full joint distribution of all the possible model scenarios. Pretty powerful. And then we just saw that mathematically, a PSHA or a logic tree is essentially an integration of probabilities across all of the possible scenarios. Hope this makes sense. Hope it helped you out. Have a great day.